So the rest of this section is going to be talking about reactions of aldehydes and ketones. Um, as we've said previously, normally we start with talking about how we synthesize them. We're not really going to do that in this chapter because we've already learned a number of methods for making aldehydes and ketones. But we will at least spend a moment briefly mentioning what those are so that we remember how to make them. In the last chapter, we covered what is by far the most important and most common way to make aldehydes and ketones, and that's the oxidation of alcohols. But in Organic 1, we also covered a couple of other methods that definitely useful, just not as important as common. So we previously talked about ozonolysis for alkenes, and then a pair of reactions that related to alkynes. Any type of hydration reaction for alkynes, as well as the hydroboration of alkynes. So here we're going to focus more on what alkyne or aldehydes and ketones are good for. And the key with carbonyls is the fact that this carbon-oxygen double bond is highly polarized. We know that oxygen is much more electronegative than carbon, and so carbonyls, basically we're looking at a partial negative on oxygen, partial positive on carbon. And we can see that even better sometimes through the use of this resonance structure, where we shift the pi electrons up onto oxygen, and we show a full positive on carbon and a full negative on oxygen. Overall, what this means for the reactivity of carbonyls, especially aldehydes and ketones, but we'll see the same thing for other carbonyls as well in the future, is that carbonyls, and again we're specifically talking about the carbon, is a very, very good electrophile. Now, of course, not every carbonyl is going to be of the same level of reactivity, and there's different things that can control it. Now, in most cases, aldehydes are better electrophiles than ketones. And so what are some of the things that have control over how good of an electrophile a carbonyl is? Well, one of the first issues is sterics. And for example, if we compare these two ketones, or even a ketone with a similar aldehyde, in order for a reaction to take place here, we have to have a nucleophile that can access this carbonyl. So we talked a lot about in the SN2 section that the more bulk, the more hindrance you put around an electrophile, the more difficult it is for a nucleophile to get in there. And while this is going to be a little bit different because a carbonyl is planar, whereas SN2 reactions we are dealing with tetrahedral carbons, the principle is largely the same. And so if we put, a large group next to our carbonyl like this T-butyl group, that's going to make the carbonyl less accessible. And if we make it less accessible, it's not as good of an electrophile. So more steric hindrance, larger groups on the carbonyl make it a worse electrophile, just like we learned with SN2 reactions. But we also have an electronic effect here. And that's electron donating groups make the carbonyl less reactive. And then, of course, the inverse is also true. If we have electron withdrawing groups, those can make the carbonyl more reactive. And this should make sense to us. If we're looking at, say, a ketone compared to an aldehyde, it becomes even more apparent if we look at a resonance structure. And specifically, we're talking about the resonance structure we saw a few minutes ago, where we put that negative charge on oxygen, positive charge on carbon. Now, why does that help us to see this? Well, in these resonance structures, the ketone is giving us essentially a secondary carbocation, where the aldehyde gives us a primary carbocation. We know, we've talked about it many times in the past, that the more substituted a carbonyl is, the more substituted it is, the more stable it is. The more stable it is, the less reactive it is. And so a ketone, which has the extra carbon group, we know that carbons are electron donating groups. That electron donating group is going to donate towards the carbon of the carbonyl and make it less reactive. So any group that can donate electron density into a carbonyl will make that carbonyl less reactive. And we can see with another example here. If we put something that now, instead of being a inductive donor like the methyl group was, we could put an aromatic ring on the carbonyl. This is, of course, a resonance donor. And it will have the same effect. The effect is that by being electron donating, the carbonyl is less delta plus, and therefore it's not as good of an electrophile. Now, that's not to say that it's a bad electrophile. Carbonyls are still almost always good electrophiles, but some, of course, are better than others. Now, with conjugated carbonyls, especially when they're conjugated with an alkene, turns out we have other factors to consider as well. And we'll get to those in the next video.